And hello, welcome back. To this video, we're going to continue talking about heat transfer, turbulent heat transfer. So in this video, last video we're talking about the turbulent Prandtl number, and we gave some arguments that by and large this thing should be equal to about 1 for a Prandtl number of about 1. Because when you non-dimensionalize the disturbances in velocities and you non-dimensionalize the disturbances in velocity and temperature, if your Prandtl number is 1, then your mechanism of transport for velocity, like u velocity fluctuations and temperature fluctuations, should be about the same. Now, if your Prandtl number varies a lot from 1, then this thing we should consider that is generally a function. Is some function of the Reynolds number. Why is it a function of Reynolds number? Because you see this U star thing over here, and of course this will be dependent on the Reynolds number. And why is it dependent on Prandtl number? Of course, because the ratio between this disturbance and this disturbance is somewhat due to the Prandtl number. In the high Prandtl number fluid, you would see more sustained peaks of temperature disturbance as compared to, let's say, the velocity disturbance. In low Prandtl number, you will see less temperature disturbances because, like I said before, I mean, one of the ways I like to think about it is that for low Prandtl number fluids, every time you have a disturbance in temperature and velocity, the temperature tends to diffuse out faster than the velocity. So that means the temperature gets conducted away faster than the velocity disturbances or the momentum disturbances. So that's how I think of a low Prandtl number fluid. For high Prandtl number fluid, the inverse is true. Velocity diffuses faster than the temperature. So we will see an inverse kind of relationship. So this is what it is in general. Okay, script P R. Okay, and this is general. Okay, of course this one could also in theory depend on these, but I would say this has a stronger relationship on these two parameters. But for Prandtl number equals to 1, okay, script P R goes to 1, okay, then this whole quantity actually goes to 1 as well. Okay, so that's a simple case. Simple case. All right. So for Prandtl fluids with Prandtl number around 1, you can make this assumption, right? And it makes the problem a lot easier. So Prandtl number equals to 1, or Prandtl number, or in this case rather, let's do for this case. For this case, okay, Prandtl T equals to this. So I'll just make that equals to 1. Then let's see the dt plus dy plus. Okay, according to this correlation from Kirillov, suitable for Prandtl number 0.7 to 100. Remember, the range is kind of limited, so that's why you don't see any Prandtl number dependence there. Or turbulent, yeah, you don't see any Prandtl number dependence there for this log law. This is a log law region. In log law region, alright. So we are only concerned with the log law region, the turbulence region and above, because in the viscous sublayer there is no turbulence, so to speak. And of course, the other analogy I want to draw, because for velocity or momentum, you have this idea. In the boundary layer, you have the viscous sublayer and the log law layer. Of course, you have some buffer layer in between, right? For temperature, you have something similar. We call this the conduction sublayer, right? Conduction sublayer, because over here the alpha T, it goes to 0, and the main mode of heat transfer is with just conduction. Okay, with just conduction, this natural thermal diffusivity. So this conduction sublayer. All right, And on top of that, you have a buffer zone and a log law layer as well. So I have a log layer over here. Very similar. So what we are doing here is to try and determine the Prandtl number in the log law region for both of these. Of course, in general, these thicknesses are not the same. The viscous sublayer and the conduction sublayer, this thickness is not the same, unless the Prandtl number is really like 1. Then okay, sure, you can live with that. Alright, so anyway, let's go back to the log law region temperature profile. This is from Kirillov for Prandtl number from 0.7 to 100. This is our standard log law velocity profile. We differentiate, okay, we differentiate del t plus del y plus, that will just be 2.075, 1 divided by y plus. And likewise for u, for the u part, okay, this is just 2.44, 1 divided by y plus. Simple enough. Okay, so on the whole, we see that we can just copy and paste these two here, and we just substitute, and that will give us a very simple correlation of a somewhat constant Prandtl number. This is about 0.85. Okay, for Prandtl number 0.7 to 100. So air has a Prandtl number of 0.71. Water has somewhere around 5. Yeah, so that's what it is. So it can be used, Prandtl number, the turbulent Prandtl number, at least here it can be set to 0.85. And experimental data kind of shows, okay, shows that using Prandtl number, turbulent Prandtl number, equals to 0.85 for this range in most Rand's equations is quite acceptable. Okay, this for Rand's equations only. So Reynolds average Navier-Stokes. Not for LES. LES has something slightly different. Okay, for LES it's different, but the order of magnitude, okay, script O of the Prandtl number, this one is equals to 1. The order of magnitude is around the order of magnitude of 1 regardless. Okay, so this is the simple way to find Prandtl number for your Reynolds average Navier-Stokes. This is the simplest case where you model all your turbulence rather than you model part of it and you resolve the rest as in LES. Now you may actually see some different correlations online, and that, for example, this correlation is actually from Bejan's textbook, from 0.5 to 5, and you can see there's some Prandtl number dependence here. But when you differentiate this with respect to y, and you have a constant Prandtl number throughout your fluid, okay, this term disappears anyhow, so it doesn't really matter. So you just have the 2.151 over y, and you just divide throughout, and then you'll get something closer to 0.9 if you use this. If you use this correlation, okay, script PRT would approach 0.9. That's what we have. Okay, so how do we get this? How do we get this correlation? It's very similar. It's very similar to our the wall the wall region correlation for the velocity as well. So you would have a constant heat flux assumption. Okay, constant heat flux assumption. So that your heat flux, you have your conduction part and then your apparent or turbulent heat flux. You add them together, it is the same as the heat flux at the wall. Okay, and the heat flux at the wall is equals to this. It's just the heat flux at the wall. Okay, Q wall. You can use Q0, that's fine. over rho Cp. All right. Of course, alpha turbulence here is 0 at the wall because there's no turbulence at the wall. Okay, so what we need to do is just to like start integrating this equation. Again, we use the same trick to replace dt with this dt minus dt naught. So let's just do that. Okay. Let's put this here. That's the exact same expression. And I can't just use for y equals to 0 now, right? I'm using it for all y because I assume this is equal. This is the assumption. We have the constant heat flux assumption. We need to highlight this, bold, underline, whatever you need to do, because that's the underlying assumption behind developing a wall functions. Okay. Anyway, so back onto this, we then want to non-dimensionalize this equation. So this of course becomes y plus, and then what do we have here? We have a y plus, and where is our, yeah, y plus. Okay, then we have a nu over u star. Okay, so let's do nu over u star. Okay, nu divided by u star. And of course, this thing I would need to replace by t plus and t star. T plus t star. Alright, and what is t star? T star, I mean, we calculated it before. So let's do it again. T star is here. And t star is this thing here. So I'm just going to do as such. So this t star equals to this, and you just substitute in. And this one I kind of leave it out because I explained this part earlier. I'll leave this out. Alright, and now we notice some things actually cancel out pretty nicely. Okay, so this Q wall and rho Cp cancel out. This U star and U star cancel out. So that's very nice for us. So this cancels out with this. Nu over 1, and then I'll have minus 1 here. Okay, very simple. Okay, very simple. Okay, if you want to get rid of this negative sign, I mean, you can. We can just define t plus in a different way. You want to get negative sign. Okay, we can sort of do it this way. Okay, t plus divided by t star equals to t wall minus t bar. That's how you, if you want to get rid of the negative sign, you can just do that straight away, no problem. You just remember to substitute back correctly later on. So we define and do the substitution differently. Okay, so we do that. And of course, we have this nu over here. Alright, nu over here, which we can just use it to divide throughout with the alpha. Okay, this divide by nu, this divide by nu. So that gets rid of the problem here. So yeah, what is this? This is actually the inverse of the Prandtl number, which is very convenient for us. 1 divided by script PR. Okay, and what is this here? Well, it's not quite the turbulent Prandtl number, but we can just do a few tricks to make it such. So we just do nu t at the bottom, nu t on top, and that will give us 1 over turbulent Prandtl number over there. So 1 divided by, okay, actually you don't need the 1 on top, so it's kind of redundant. But, oopsie, I can do it like that, just to make it look nice. Script PRT. Alright, so that's how we get this so-called equation out here. Now, of course, then we can bring this to the right hand side. Okay, bring this to the right hand side. So I'm just going to cut this. I'm going to paste it here. Okay, and now we can try to integrate for t plus profile, right? T plus equals to integral of 0 to whatever y plus you want. Okay, so dy plus prime. So I'll use that as a dummy variable. Okay, because if you just integrate like this, if you just integrate like this, it doesn't like, mathematically, yeah, you understand what I mean, I hope, but it kind of doesn't make sense. So somehow you want to use this dy plus prime as a dummy variable. Okay, so we can do this sort of thing. Right, so next we can sort of separate out this this integral into two parts, right? All right, so we have a case. Now we have a case in the viscous sublayer, or in the viscous sublayer, so to speak. All right, this new t approaches 0, which makes sense. Okay, and this term disappears compared to 1 over Prandtl number. Okay, this we call this, in this regime we call it the conduction sublayer. Alright, so it's somewhere, closely related to the viscous sublayer, but the layer thickness kind of differs between both of them. So we have two regimes, right? One in this conduction sublayer, and then the other regime is where, you know, your this term becomes so big. All right, yeah, where this term becomes very big. It's much bigger than 1 over the Prandtl number. So that occurs, that usually occurs when nu t is much greater than nu, and we know turbulent Prandtl number is on the order of magnitude of 1, as we've seen before, but that's kind of from experimental data anyhow. But anyway, so if you have nu t much greater than nu, or much greater than nu times the Prandtl number, turbulent Prandtl number, then we have this log layer. We have a log layer regime. Okay, so let's break this up. Okay, let's break this up into two integrals. Okay, so first integral is to the conduction sublayer, and this is from Bejan's book. Okay, first is to the conduction sublayer, and one is from the conduction sublayer onwards. So this is kind of a patchy way of thinking of the it's a way to think of the boundary layer here. Of course, we kind of ignore the buffer layer, which in reality there is, but this is just a mathematical model to help us, you know, simplify and make sense of things. So in the conduction sublayer, of course, this term disappears. In the log layer region, this term over here disappears. So we have two regimes. So this one is pretty straightforward, because Prandtl number, by and large, it's constant. So we can bring this constant out. P, script PR. Alright. So the first one we have an integral from 0 to YCSL. So we have this YCSL. Okay. So in the conduction sublayer, okay, we'll have this correlation going on. Okay, y plus from y plus equals 0 to y plus equals to y CSL plus. Okay, so where is this y CSL? You have to kind of determine it by experimental data. So in the log law region, so to speak, okay, where y is from YCSL onwards, this term disappears, and then we have something like this. Yes, but then how do we integrate this term over here? Well, the way to approach it is to consider this new t term. Okay, this new t term. Now, the thing is, how do we get this? We need to get it from, you know, how we got our momentum sublayers from. Okay, so recall when we derived our log law region for velocity. So this was many videos back. I hope you still somewhat remember. So 1 plus nu t divided by nu, okay, partial u plus partial y plus equals to 1. Okay, so in log law region, we'll just have this equation. This nu t over nu is much greater than 1, so I'll just bring it over to the other side. So you have nu divided by nu t. Okay, nu divided by nu t over there, and what we can do is just substitute this in over here. So this is du plus dy plus, okay, 1 over, okay, du plus dy plus. And what is du plus dy plus? Alright, what is du plus dy plus? Okay, well, it's in this log layer region we have du plus dy plus. Okay, in log law region, du plus dy plus is equals to, right, if you can remember, you know, this is what roughly our log law equation looks like. Okay, so du plus dy plus here, you just differentiate. Okay, about 1 over 0.41 and 1 over y. So was that 0.41 is actually, okay, 1 equals to 1 divided 0.41, 1 divided by y plus. This is actually the von Karman coefficient. Okay, and you might see it written like this also, kappa y plus, where kappa is this von Karman coefficient. So that's, we can substitute in again, and that will roughly land you where we need to be. So many divisions here, kind of losing track. This should go here, and this should just be at the bottom. Okay, so von Karman coefficient should be it should be constant. Okay, von Karman coefficient should be constant, and this turbulent Prandtl number, okay, we kind of assume it doesn't really change much, so we just bring the turbulent Prandtl number out and the von Karman coefficient out. Of course, in reality, when you do those DNS and everything, it might change from time to time, but for Reynolds average Navier stock, since we kind of take a statistical average over time, that should not really matter too much. So what you have left is this logarithm looking region, and therefore you will have just the natural logarithm of y plus divided by y CSL plus, where CSL is this conduction sublayer. Okay, so this is how we get that equation. All right, so we can get script PRT from these equations and compare to experimental data. All right, so this is for log law region, and this is for the conduction sublayer. All right, okay, conduction sublayer. All right, so that's how we got it. And if we substitute, right, okay, where's this yeah, we substitute and we compare with experimental data, substitute script P RT equals to 0.9, y CSL plus equals to 13.2, and one more thing is kappa, the von Karman coefficient, equals 0.41. That will give you this equation here. Okay, that results in this equation for Prandtl equals to 0.525. So that's the theoretical background behind developing Prandtl number for the sublayer region. Okay, the boundary layer region. So this is how we get an estimate of Prandtl number equals 0.85, 0.9, what have you. Remember, when you differentiate this 2.195 just comes out. You use that and you do the same substitution here. Okay, you do the same substitution here. You should get Prandtl number of 0.9, because you have this 2.195 in the numerator. It should be bigger. Alright, anyway, so thanks for watching. I'll see you guys again in the next video. Bye.